Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Physics Paper 1 Higher Tier from 2019. Question number 6 is on the topic of atomic structure. Lanthanum 140 is a radioactive isotope. A nucleus of lanthanum 140 emits gamma radiation. What happens to the mass number and the charge of the nucleus when gamma radiation is emitted? Now, gamma radiation, just given the symbol, is a EM wave. So there's no particles actually being lost. That means the mass number and the charge number should stay the same. Why is it difficult to detect gamma radiation? Now, the reason it is difficult to detect gamma radiation is because it's only weakly ionizing, and even if it's presented in front of a detector, it's so fast it actually is very hard for the detector to detect it. So that's actually two reasons. So since gamma radiation is only weakly ionizing, right? Or you could say most gamma radiation will pass through the detector undetected since they are fast. The activity is the rate at which a radioactive source decays. A teacher measured the count rate from a sample of lanthanum 140 using a Geiger-Müller or a GM tube. Explain why the count rate was less than the activity of the sample of lanthanum. Now, let's say you have a radiation source, which is a rock, and it's going to give out radiation in all directions. You're going to have a GM tube, which is connected to the probe. So that's the counter, and that's the probe. So the amount of radiation that is coming through into the probe is actually going to be very less. You're not actually detecting all the rest of the radiation. So since radiation spreads out in all directions, only some of the radiation goes in to the GM tube. The teacher investigated how the thickness of lead affected the amount of radiation, gamma radiation, that could pass through it. So you have figure 6 shows the apparatus. You have the sample of lanthanum 140 in here, and that's going to come forward, and you got the lead, and you got the GM tube in front of it connected to the counting machine. Explain why the teacher stood as far away from the apparatus as possible. That's mainly because gamma is highly penetrating and it has a bigger range. But explain why. So that's actually a precaution the teacher is actually taking. So you need to talk in terms of that. To reduce the amount of radiation received, since radiation increases the risk of cancer or genetic mutations. .5. Table 1 shows the results. Thickness of lead in centimeters, so it's increasing by 0.5 centimeters all the way up to 2.5 centimeters. The count rate started at 110, drops down to 10. So as the thickness increases, the count rate per second is decreasing. So the teacher concluded that the count rate was not inversely proportional to the thickness of the lead. Explain why the teacher was correct. Now, they're asking, the teacher concluded that the count rate was not inversely proportional. So what does that inversely proportional actually mean? To the thickness of the lead. So if it was directly proportional, when one value doubles, so from 0.5 to 1, if that doubles, then this should also double. Inversely proportional means when this doubles, this should half. So if I multiply the thickness multiplied by the count rate, I should get a constant value if it was inversely proportional. So let's multiply 110 by 0.5, that would be 55. Multiply 1 by 60, that is 60. Those two values are not the same. 1.5 times 3.33 is 50. 2 times 18 is 36. 2.5 times 10 is 25. So as you can see, all these values are different, so it cannot be inversely proportional. So how do we write the answer for this? You can simply write the answer as the calculation. Since product of thickness and count rate is not constant. Example, 0.5 times 100 equals 55. 1.0 times 60 equals 60. You just need to give two calculations, but let's do three calculation. 1.5 times 33 is 50. So these values are not the same. Lanthanum 140 can also emit beta radiation and change into cerium. Complete the equation showing the decay of lanthanum La 140 into cerium Ce. So because it's an electron, beta radiation is a fast moving electron. It would have 0 mass and a charge of -1. Then we can work out the mass for this cerium. The mass would remain unchanged, 140, and the proton number would actually be one more than what it started off, so it will be 58. There are other isotopes of cerium that are radioactive. Different isotopes of cerium have different half-lives. The half-life of an isotope can be found by studying how the number of atoms changes over time. Figure 7 shows how the number of atoms of cerium 148 in a 120 gram sample changes over time. So you're starting off with 120 grams, and at the start the number of atoms of cerium is 10 to the power 23, so that's 5 times 10 to the power 23, and after 100 seconds it's 1.25 times 10 to the power 23 atoms. Okay, let's have a look at the question. Determine the ratio of the number of cerium atoms in the sample when it was 100 seconds old compared to when the sample was 350 seconds old. So how they haven't actually given the graph up to 350, which means you have to work it out. Now, what was the half-life? Right, let's work out the half-life first. Starting at 5, right? Let's ignore it's 10 to the power 23 for now. If we start at 5, for it to fall down to 2.5, it's taken exactly 50 seconds. So from 2.5 to 1.25, it's taken 100 seconds. So that's actually 2 half-lives. So let's say half-life equals 50 seconds. So we start at 5, it's still multiplied by 10 to the power 23, it goes to 1.25, and then 0. Let me get my calculator out. So 1.25 divided by 2 will give me 0.625. Going on to divide that by 2 again, 0.3125, divide that by 2 again, 0.15625. So every single time it's 50 seconds, so that will be 100 seconds, 150 seconds, 200 seconds. So I need to go down 2 more, so up to 350 seconds. So let's divide that value by 2 again. It'll be 0.078 that will be 250 seconds. So divide that by 2 again. I'm going to come this way. 0.0391, divide that by 2 again, it will be 0.01953. Okay, I write the full number 125 as well. So I think we've done 350 seconds, 300 seconds, 350 seconds. So we've gone through 1, 2, 3, 4, 5, 6, 7 half-lives. Right, let's see if this works. So at the start we are trying to work out the ratio of the number of cerium atoms in the sample when it was 100 seconds, compare that to 350 seconds. Okay, so we are not actually starting off at 5, are we? So at 100 seconds it should be this number, 0.625, and 350 seconds it's this number. So I need to find the ratio of those two. So if I divide 0.625, so if this is for 100 second is to 350 second, divide that by 0.019531. Let's see, 0.625, divide that by 0.019531. That gives me 32.00008. So I'll take it as 32. So that ratio is 1:32. 1:32. Now there are other ways that you can actually do this as well. If you look at the marking scheme, they show it in a slightly different way, but I think this is actually the best way, rather than complicating it too much using fractions and such. So last question, determine the activity of the sample of cerium when the sample was 20 seconds old. For 3 marks, use figure 7. So which means you will have to wind up drawing a tangent on the graph at 20 seconds. So you're not going to be able to, you can't simply work out, oh, that's 20 and I'm going to read out from there, because they are asking for determine the activity of the sample. Okay, so at 20 degree, 20, let's say if I draw a straight line going through that, I can draw a straight line. Here, try it again. It's a different color. Okay, so I've got slightly change the orientation for that. Bring that down. Okay, so that's slightly off, which is fine. So if I take the value here, say 4.8, 4.8, and here it's 2.5, so that's 2.5. So the y value is 4.8 minus 2.5, that's 2.3, and the time or the x value is 40. So two point 3 divided by 40 is equal to 2.3 divided by 40 is 0.0575 times 10 to the power 23. So writing the answer properly, it will be 5.75 times 10 to the power 21 becquerels. So the accepted answer is, what they have given from the gradient is 5.3, but they have given a range between 4.7 times 10 to the power. So if your answer is, let me show you the marking scheme. As you can see, you need to draw a tangent on the graph, use the gradient, and that's the given answer, but allow a range between 4.7 and 5.9 times 10 to the power 21. Our answer is 5.75 times 10 to the power 21. That brings us to the end of this question and to the end of the video for this paper. Thanks for watching, and if you find this useful, check out my channel EduWise 101 for biology and chemistry papers, and all the other papers from AQA from the other years, both for combined and for triple science, including the foundation papers as well. Thank you.